do start off with exponents and just some like math 10C exponent rules. So the exponent rules that we mainly focus on are the product of two things and the division of two things, but we're going to look at all of them. So the first exponent rule that we need to remember is that if you have two bases the same and they're multiplied together, then you can add their exponents. Okay, so two bases have to be the same. We can add their exponents. So it combines to just be a and then m plus. Alternatively, if you were to be dividing, I should have put this in the second one. No, I didn't. If you're dividing two bases that are the same, you can subtract the exponents, right? So multiply, add, dividing, subtract. Other rules that apply that we just need to kind of remember is the power of a product rule. So that means the power of a power rule. That means if you have an exponent that also has an exponent, the exponents multiply together. So it would become a to the power of m times m. Oh, you just look really upset. So not bad for you. The same rule applies to these two, where the exponent really, it just comes in. So like this n is going to come to both things, and it's going to multiply to the exponents of both things. So this would be 1 times n and then 1 times n to become a n bn. The exponents just come into the brackets, assuming that inside the brackets there's no addition or subtraction. If there's addition or subtraction, then those rules don't work. Another one, and this is kind of the big one that's difficult that we do a lot of, is negative exponents. So negative exponents, we change to positive exponents by turning the entire power, so this thing would be a power, into a fraction. So this entire power goes underneath 1. And then the exponent turns to a positive exponent. And we are going to utilize that rule a few times. Okay? So you can change if an exponent is positive or negative by changing it into a fraction or out of a fraction. Like I could have gone the other way with this too. If I wanted to change this into a negative fraction, I could have gotten rid of the fraction and made it a negative exponent. So you can go both ways with these rules. I could break things up or bring them together. The last two rules, anything to the power of 1 is just itself. Anything to the power of 0 is 1. That's one people tend to forget. Anything to the power of 0 equals 1. That one's a hard proof to explain. People usually get stuck on it. Imagine if you had x squared divided by x squared. I know that's going to equal just 1. Right? X squared divided by x squared is the same thing. Same thing divided by itself is 1. Or I could do my subtraction rule, which means x to the power of 0 equals 1. So that's kind of how you could prove this one if it made you feel better. It would still be 1. Anything to the power of 0 is 1.
That just logically makes sense. That 0 could use something.
Yeah, but exponents are talking about multiplying something by 0 things. That's why it wouldn't make sense. Again, exponent of 0 is a hard thing to comprehend. That's why it's best to just think of it as like this to be able to get yourself there. Anything to the power of 0 is 1. The other thing that we might run into, which I doubt we'll run into, is fraction exponents. Fraction exponents can be rewritten as square roots, where the bottom of the fraction is the index. I doubt we'll do much with that. It might pop up, so we talk about it. But it's really, if it comes under a formula, it's a pretty hard question. I don't think it will. You never know. Okay. Practicing. So, we're going to go through, you can do it on your own. Give it a shot. See what you can do. Try to simplify all these things into single powers. Don't worry about evaluating them, like actually figuring out what the numbers are. Just try to write them as single exponents. Okay, so this first one, for instance, I have 3 to the power 4, it's 3 to the power 2. I add the exponents because it's multiplying, so it's 3 to the power of 6. So try your absolute best. So if we go through these, I'm going to rip through them. If you have a question on one of them, just stop me. This second one, that would be power of a power. So that means the 3 comes in, it multiplies by the 2 to become 2 to the power of 6. The next one, look at this. It's a division problem. So that means we're subtracting the exponents. So it would be negative 2 to the power of 3. 5 minus 2 is 3. For d over here, this is multiplication, so we add the exponents, so it's b to the power of 7. The next one, multiplication again. This exponent is a 1. Remember, if there's no exponent, there's a 1 there. So it'd be 6 plus 1 would be x to the power of 7. F. There's 2 ways you could do f. This is multiplication. It's a multiplication of 3 things. So you can add all the exponents, which would be b to the power of 11. Or you can understand that b to the power of 0 is just equal to 1. So it basically goes away. And then you could add b to the 7 and b to the 4, be b to the 11. And it would still be times 1, but we just don't write times 1, right? No, just makes that power 1. For g, the exponent comes in, you multiply, so it's a to the 12. Down here, it's subtraction because it's division. However, these are different bases. This is a j and an h. So you cannot combine those into one thing because they're different bases. What you could do is you can make these positive exponents by flipping where they are. So the h to the 5 goes to the top, the j to the 8 goes to the bottom. Now you have positive exponents. For I, that's a division problem, so you're subtracting the exponent, so it's y to the 6. For j, the 6 is coming into the brackets to both things, so it's s to the 6, t to the 6. And the last one, the 4 comes to the exponent. It goes to each thing. The negative 3 I leave in brackets to the power of 4 because it matters if there's brackets or not. If you don't put a negative sign, if you don't put brackets, the negative sign would stay there. If you do put brackets, the negative sign ends up getting canceled out when you calculate. So then brackets around the negative 3 do matter. Okay, those are exponent laws, pretty basic exponent laws. You need them to be able to do part of your practice booklet. We don't use them too much during the lesson, but you should be able to use the exponent laws to answer questions in your practice booklet. What we're going to do is we're going to start solving some questions where we don't know what the exponent's equal to. So if you look at questions like this one, you'll see we have 4 to the power of 2x equals 4 to the power of x plus 1. And your job is going to be to solve that for what x equals. Now, up until this point in time, you don't want to write this, but you guys have seen things like 2x equals 4. And you'd just be like, oh, divided by 2, divided by 2. Sometimes you guys have seen things like x to the power of 2 equals 4. And you'd be like, well, square root, x equals 2. Like you've had all types of questions. You could have seen things like 3 divided by x equals, let's say, 9. And then you multiply the x over here, divide the 9 over there. Right? You've seen every type of question, except you've never seen when x is the exponent. So this is the first time that it's going to be solved for x, but x is in the exponent.
Didn't we have x in exponents in your 10?
No, you shouldn't have. You did have variables in the exponents, but you weren't solving for them. You might have just had like a variable. So what we're going to do is we're going to solve these using like bases. You'll notice that the questions that we start off with, like on this page, the bases are the exact same. I have 4 to the power of 2x equals 4 to the power of x plus 1. If the bases are the same, that means if I can make the exponents the same, then both things would equal each other. So I'm going to write out 2x equals x plus 1. If I can make the exponents equal the same number, then that means the whole powers would be the same powers. Kind of makes sense, right? If I say 4 to the power of 2x equals 4 to the power of x plus 1, of 2x equals x plus 1, then that would make the statement true, because that means they would both have the same exponent. It could turn into maybe 4 to the power of 10 equals 4 to the power of 10. That would make sense. So because their bases are the same, all we have to do is solve the exponents and make that a separate little equation. This is something we've solved before. So we get all the x's to one side, so x equals 1. If you tested it, it should work out. So if I put 1 into this equation, it would give me 4 to the power of 2 equals 4 to the power of 2. See how that worked out? 16 equals 16? Definitely true. 4 squared equals 4 squared? Definitely true. So when the bases are the same, you can just focus on the exponents. We'll try it again right here. It's a little more challenging, but still we notice that it's 10 and 10. That means we can look at just the exponents and make those things the same, and then the whole statement would be true still. So let's say 3x minus 4 equals 6x minus 1. That's a linear equation. To solve linear equations, move all your x's to one side. So negative 4 equals 3x minus 1. And add 1 to both sides. Negative 3 equals 3x. Divide both sides by 2. Negative 1 equals 3. Again, you can test that out. Put negative 1 into your equation. See if they actually equal the same thing. They would. So I moved all my x's to one side. I subtracted 3x from both sides. It gave me negative 4 equals 3x minus 1. Then I moved my constants to the other side, so I added 1 to both sides. I had negative 3 equals 3x. And then I divided both sides by 3 to get x by itself. All right, last one. Same situation. The bases are the same. So that means I can just say if x equals 11x minus 20, I can solve that. Move all my x's to one side. So subtract x. I'm going to add 20 to both sides. So 20 equals 10x divided by 10. 2 equals x. This is a strategy that works if the bases are the same. I understand I'm doing the algebra fast, but I have faith you can do the algebra. Bases are the same, just focus on the exponents. I want you to try the next 3 on your own. Give it a shot. We realized they were both base 9, so I don't need to worry about the bases. I just need to solve the exponents. X equals 2x plus 1. I get all my x's to one side, divide by, divide by this one. Just subtract. In the middle one, I realize my bases are the same. I have 121 and 121, so they really don't matter to me. All I need to focus on is the exponents equaling each other. So 2x minus 7 equals 4x minus 1. Move your x's to one side, your constants together. The last one, same thing. I have 2 to the power of negative 2x and 2 to the power of x minus 18. The base is the same. I don't need to worry about them. I just make the exponents equal the same, and then the whole thing will work out. Alright, it's nice when you get a question like that, where the bases are the exact same. Unfortunately, that doesn't always happen. So instead, what we're going to have to do, and what we're going to have to get good at in practice a lot, is getting same bases. So you're going to hear me talk to you about get a like base, get a similar base, get the same base. I'm going to use different terminology for saying you have to have the same base to be able to solve a problem. Because if I looked at this here now and I said 2 to the power of 2x equals 4 to the power of x plus 1, and I said, well, let's just make 2x equal x plus 1, and I solve that thing to say x equals 1, that's not going to work. Because 2 squared equals 4, which does not equal 4 squared, which would be 16. That doesn't work. So instead, your first step is going to be to get the same base. To do that, you're probably going to have to know your exponents pretty decently. I would suggest that you know your first like 10 perfect square numbers. Perfect square numbers, you've been doing since math and see. Perfect square numbers are when you go 2 squared equals 4, 3 squared equals 9, 4 squared equals 16, 5 squared equals 25. And I suggest that you know the first like 10 really well. Maybe the first 12. Every question that we do where you need to get a like base is going to have one of these numbers. Oops. 100 squared is unable. Squared does not. These numbers are your perfect square numbers. 4, 9, 16, 25, 36, 49, 481, 100. You can keep going, right? 11 squared is 121, 12 squared is 144. You should know the first like dozen. The reason those numbers are going to be important is we're going to break those numbers down. So if you look at this question right here, we see we have 2 and we have 4 as our bases. I can rewrite 4 as 2 squared. So now I have 2 to the power of 2x equals 4, 2 to the power of 2, power of x plus 1. So you notice that I've rewritten 4 as 2 to the power of 2, and I put it in brackets. The reason I put it in brackets is now I want to rewrite this thing as a single power, so that I have like bases with a similar power. That means a singular power. That means I can do the same thing I was doing on the other slide. So when I have a power of a power, it multiplies in. I have 2 to the power of 2x equals 2 to the power of 2x plus 1. Everybody see how I got that? So I got a similar base by breaking down my perfect square number, and then I multiplied my exponents together. So the x came in and the 1 came in.
So what is it, 2?
Solving this thing's going to be hard. Yeah.
2 or 2x plus 1?
It'd be 2x plus, did I put 1? Sorry. Glad you said that. At that point, you have a question just like the slide before. You now have a similar base, so you can focus just on the exponents. If you tried to solve that thing, you'd move all your x's to one side. What happens when I have 2x minus 2x? So that means 0. Oh, man. 0 equals 2. Is that possible? So if you end up with something like that, that means you have no solution. So this question would not actually have a value that would make that work. There is no value of x that would make both sides equal to each other. All right. We're going to try on B to get like bases. To do that is hard sometimes. The number 9 is a perfect square number, correct? The number 9 should be broken down into 3 squared. I'm going to put it in brackets, and it's still going to be the x to the power of negative 4. 27 is not a perfect square, but it is a perfect cube. So now with these numbers, you need to know the perfect squares, and then you need to know what would happen if I did perfect cube. So it would be 8, 27, it would be 64, it would be 125, And then I lose track after that. To know them all by heart, not really. But you can calculate them to try to figure them out, right? I'll give you a hint, and this is how I usually figure them out. One of them is usually easy, like 9. I knew that one. That easily changes. The only way I could do this question is if I had a similar base. So 27 must turn into 3 somehow, and it's got to. So you can usually, if you can figure one of them out, try to use that intuition to figure the second one out. Doesn't always work, but when it works, it's nice. So 27 could be rewritten as 3 to the power of 3. And then the x minus 1 is still x minus 1. Now you have similar bases. You're going to use your exponent law to multiply these things together. So 2x minus 8 is going to equal to 3x minus 2. Okay, all I'm worried about is the exponents. I had to multiply because it was a power of a power, and they had to be equal to each other. So in one step, I turned that thing into 2x minus 8 equals 3x minus 3. If you solve that thing, you have a little more room on your paper than I do, you should get negative 5 equals x. So I move my 2x to the right, I move my negative 3 to the left, negative 8 plus 3 is negative 5, 3x minus 2x is 1x. Alright, last one. If you look at this question, this one's a fraction, so it's a little bit trickier. The first thing I'm still going to do is try to get like bases with it. So I'm going to look at these constants and try to turn them into like bases. 8 turns into 2 to the power of 3. 4 turns into 2 squared. So I'm going to have 1 divided by 2 to the power of 3 equals 2 squared to the power of x minus 20. No. That's a lot. You could, but you'd have to do something to it. We're going to do that right now. So if you looked at this right now, I've turned both of these into 2, which is good, but it's still not the similar base. The reason it's not the same base is because this one is a fraction and this one is not a fraction. So making these the same would not work out. So what I need to do is try to get rid of this fraction. To get rid of the fraction, I'm using the negative exponent law. So if I moved this to the top, it would become 2 to the power of negative 3 equals 2 to the power of 2x minus 4. So to change this, I had to make the exponent as negative 3. That's our negative exponent law that we talked about. Similar base was good. It was 2, but you have to have it in the same form. What Hannah said was, could I make this thing a fraction? And you could, but you'd have to make the whole thing a fraction, and it becomes much harder. Much easier to turn something that's a fraction into a non-fraction. Makes your life much easier. Now you've got your setup where you can just focus on the exponents. If you were to solve that thing, you're going to end up with 37 over 2. All right. You have 3 here for you to practice on your own. Give it a shot. I'll go over them after, but try your absolute best, okay? A, like I said, can be done 2 ways. I did it making the bases 2. You could do it making the bases 4, because 16 is 4 to the power of 2, and both the bases would be 4. Okay, so there's multiple ways to do some numbers. 4 and 16 is a common one. You could also end up with, I think 16 or something works out nicely too. 16 and 64.
Yes. It's on the board.
Yeah, but I'm trying to think of what their perfect squares are. It's 4 and 8, right? You squared at 16, so you squared at 64 and 8. Sometimes you turn 64 and 4. Just depends on the question, right? So there's different ways to do some of these questions. Either way, you should get x equals negative 8. Yeah.
Is it better to go smaller, like a bit?
No, to me it's better to do it with 4. Like, my reason would be then you have less multiplication and smaller numbers to deal with when you're solving the exponents. So I think the better way to do that, it would be 16, turning it into 4. The second one, the left side, you only had to change 11 or 121 into 11 squared. That's not in the first 10, but 121 and 144 are probably both fair game that you'll see quite often. You might see 169, which is 13 squared. At the end of the day, you can keep calculating more and more if you want, right? Like, I can check to see if any number is a perfect square by just square rooting it. If the square root of 121 equals a whole number, then it's a perfect square number. So you can check numbers. You don't have to have anything memorized. You can always check. The last one's definitely the hardest one. So I changed that fraction into not a fraction by making it a negative exponent. You have to do that to be able to do this question. So I turn that thing to negative 8x so that it's no longer a fraction. On the right side, I changed 25 to become 5 squared. I have like bases. I can solve that problem. Awesome. Now, questions that aren't on here, that could be on here. I'm just going to insert a blank page so I can show you an example of what I mean. You could end up with something like this. 2 to the power of x times 2 to the power of 2 equals 2 to the power of 4. So we did those exponent rules for a reason. Like bases is great, but it has to be a singular like base. So this would change to be 2 to the power of x plus 2 equals 2 to the power of 4. Right? If you're multiplying bases, you add the exponents. So I just kind of expect that you should be able to do that. But you might see that in your practice book a little bit, where you need to combine them into one fraction. By one fraction, I mean one power. And then solve the exponents. So a question like 125 to the power of x divided by 5 to the power of 2 equals 125 to the power of 3. Like, that's a question you should be able to do. Make it a similar base. So this becomes 5 squared x divided by 5 squared equals 5 squared to the power of 3. And then combine into a singular. So this would be 5 to the power of 2x. 5 to the power of 2x minus 2. See how that combines? You multiplied the x, and then you subtracted because it was division. So you should be able to combine exponents using your Math 10C exponent clause. The x and the 2 multiplied together, and then you subtract by 2 because it's division. Equals 5 to the power of 6. So we don't do any of those together. There's not a lot of them. It's definitely something you should be able to do and be able to handle them. You're just using your Math 10C exponent laws to create singular powers. The similar base is the new skill. So creating a same base, that's what you should be brand new to. Tomorrow what we're going to do is we're going to learn what to do